Now we look at this topic, the conservation of momentum. Now momentum has been defined as the product of mass of a body and its velocity. Okay, momentum is the mass of a body in motion. Sometimes they call it the amount of motion. So when the body moves along a straight line, let's say a body of mass m moving with a speed v, as long as no external force act on this body, such that it's possible to keep the speed of the body constant, it means that the momentum of the body will not change. Of course, you know, according to Newton's first law, that a body in motion remains in motion as long as no external force act on it. When the external force comes in, it alters the speed of the body, changes its velocity either by increasing it or by reducing it, and thereby momentum of the body will change. But when the external forces are removed, no external force acting on the body, it means that the momentum of the body will stay constant. Constant. So it means that change in momentum of a body over time will be equal to zero if there is no external force act. And recall that Newton's second law of motion states that the external force that act on this body is equal to the rate of change of the body's momentum. So if I keep the momentum change, or that is if it is zero, or if I keep the momentum of the body constant, it means that there is no force acting on it. Because when the momentum is constant, the change in momentum will be zero. Constant means momentum does not change, and therefore no external force act on it. Now, how do we apply this conservation of momentum to a system of colliding particles or system of colliding masses? Let's take, for instance, we have two masses. You know, the masses are M1 and M2, and these two masses move with initial speed U1 and U2 in the opposite direction towards each other. And after some time, they collide. Let's say, suppose that after they collide, they move off each other with the final speeds V1 and V2. Okay, these are initial parameters: initial speed of the first mass, initial speed of the second mass, the final speed of the first mass, the final speed. This is what happens, or their speeds after the collision. Okay, you are going to see that in the course of collision or during collision, let's say these are the two masses, each of them exerts a force on the other. Okay, maybe I should label the force. Let me call this mass 1 or mass A and call this mass 2. Now, let me call this one F12. F12 is defined as the force on this mass 1 due to the second mass. And I know it acts in this direction because this F12 is coming from this mass 2, so it must act in this way. Now, also, during the course of collision, this mass 1 will exert some force on mass 2, and that one act this way. We can label that one F21. So what is F21 again? The force on mass 2. First of all, we label the particular mass force. Then this one means coming from mass 1. Okay, according to Newton's third law of motion, you can see that coming to momentum conservation, the three laws of motion, Newton's laws of motion play out. The first law, I already said that provided no external force act, a body's mass, a body's speed remains constant. And because the speed remains constant, it means its momentum does not change, provided no external force act. Okay? And I also said that for Newton's second law of motion, that for a body to experience a force on it, its momentum must change. Or whenever the body's momentum changes, an external force acting on it. So when momentum changes zero, it means the momentum of the body is constant, no external force act. And this is a case of two masses in collision. Now let's see from Newton's third law. Of course, Newton's third law of motion states that to every action, there is always an equal and opposite reaction. That is, in the course of collision, okay, the force that mass 2 exerts on mass 1, I can call that my action. Okay, let me call F12 my action force. My action force, okay? Remember, action is the type of force expressed in Newton, not a type of action in drama and all that. This is action in physics. All right. So now, in the same vein, the second mass also receives some impulse from the first mass. I can call that F21. That is a force on mass 2 due to mass 1. I can call that reaction. So what Newton's third law is saying that during collision, and for the fact that the two masses exert a force on each other, it means that in terms of magnitude, the two forces are equal. That is, F12 equals F21. But in terms of direction, the two forces act in a direction such as they are opposite to each other. That is, F12 equals the F21. So that if I bring this to this side, it means the sum of the forces F12 plus F21 is equal to 0. Now, when the resultant force, because since the two forces are equal, and they act in opposite direction. Of course, their resultant, talk about it, think about it again, their resultant is the difference between them. The resultant will definitely be 0. Supposing that F21, for instance, is 10 Newton. Of course, from Newton's second law, from Newton's third law of motion, it means that F12 will equally be 10 Newton. So that since they act in opposite direction, what's the resultant of the two forces? I've taught resultant. I took some time to explain how to find the resultant of two forces, irrespective of the directions they are acting. So resultant force gives 10 minus 10, which is 0. So that means that when two masses collide, no, they exert a force on each other. But to come to see that the resultant force on the system of masses is also 0. So when there is no external force acting, for instance, if these two masses move towards each other, one source of external force may be the frictional force that acts. Let's say this is the case now where these two masses are moving towards each other. This is mass 1, this mass 2. A source of external force may be the resistance to motion offered between the mass and the surface, the floor. But if this external force or frictional force is removed, you see, and we are saying that when the two masses collide, they exert the same force on each other. And the resultant force on the system, F, is equal to 0. It means that the momentum of these masses would not change during collision, provided no external force acts. The momentum of this system of colliding bodies will not change. That's what we're saying in essence. Okay, so we can write from Newton's second law and third law of motion, derive an equation for this, the momentum of this system of colliding bodies. Okay, so okay, let's say this is a case before they collide. Let me label this as M1. Okay, label this as M2, label this as U1, label this as U2. Okay, in the course of collision, of course, I've labeled this already. This is my F12 and this is my FM21. Okay, then after the impact, let's say they collided along this line. After the impact, we expect that M1 moves away if the collision is elastic. They did not stick to each other after the collision. This mass 1, this mass 2. This one moves away with V2, which is momentum after collision final is M2 V2. Momentum of this one, let's say this one moves away with speed V1. Its final momentum is M1 V1. Of course, and also write the expression of the momentum of this mass 2 initially. That's M2U2, and this one is what? M1 U1. Okay, so during collision, the momentum of this mass 1 will change. Let's call that delta, momentum, delta P1 is momentum change of this. So it's going to be equal to the force applied, F12, the force that acted on it, multiplied by the time taken for the change. Of course, you know that force is equal to momentum change over time, okay? Momentum change over time. So that's what I've just done here. To find momentum change, we have to cross multiply. That gives us that. And then for the second mass, momentum change of the second mass, P2, delta P2, will give us F21 times delta T. Now, this delta T is defined as the time of impact. That is the contact time. The time during which the two balls or two masses were in contact together. That is why the collision was taking place. So, we call that the time of impact, or the contact time, right? Now, we have this and this. So that from Newton's second law of motion, or from Newton's third law of motion, we have that F12 plus F21 is equal to 0. So my F21 is momentum change over time, delta t. From here, my F21 momentum change over time, plus what's my F21? Momentum change of the second ball over 2 over time is equal to 0. Now, since the time is the same, so I'm going to cancel out this. It means that momentum change of the first mass plus momentum change of the second mass is equal to 0. What does it tell us? That their momentum is conserved. Okay, so from here we can see the momentum change is equal to final momentum of the first mass m1 v1 minus the initial for this m2 m1 u1. Okay, that is for the first mass. Okay, then plus for the second mass we have m2 v2 minus m2 u2. Okay, equal to 0. Okay, so from here I have m1 v1 minus m1 u1 plus m2 v2 minus m2 u2 is equal to 0. So if I collect like terms, now I'm going to have m1 v1, I have that m1 v1 plus m2 v2 is equal to, take these two terms to the other side, I have m1 u1 plus m2 u2. Okay, so that tells us that there is no change in the total momentum of this system of colliding masses. Their total momentum before collision, which is m1u1 plus m2u2, remains the same. That is equal to their total momentum even after the impact, even after the collision must have taken place. So there's no change in momentum. So this gives the principle of conservation of momentum, that for a system of colliding bodies that are isolated, no external force act on them, that their total momentum is constant. By extension, the sum of their momenta before collision is equal to the sum of the momentum after collision. Okay? So in the next video, we shall apply this principle to solve questions. Thank you.